last speaker of today is Professor Marcos Katz from the University of Oulu. And Marcos has been working with visible light communications and communication networks for many years. And will be talking about indoor energy networking, a path to sustainable zero energy IoT and 6G critical infrastructure. So, welcome, Marcos.
Yes, good afternoon. Indeed, I will be talking about IoT, a subject that has not been widely discussed today as a part of 6G. And so this talk is kind of focused on the intersection of resilience and sustainability. And in IoT, particularly in zero energy IoT, meaning those IoT systems which are based only on the ambient energy that they can harvest. And so IoT is a key essential element or backbone in infrastructure, and IoT nodes are sensing, actuating, sending information, processing information. Today in the world there are, according to some estimations, several tens of billions of IoT devices. In general, those devices use batteries for operation, and those batteries, of course, we need to manufacture them. Every now and then we need to replace them, and then we have, at the end of the lifetime of the battery, we need to throw them, dispose of them, and this is not a sustainable solution. And over the last years, the concept of zero energy IoT has become stronger, and as an example, in February this year, the Ambient IoT Alliance was established to particularly promote zero energy IoT, and you can see that there are really big players like Intel, Qualcomm, Pepsi as a founder members of this. So harvesting energy from the environment, do we have enough energy to operate with that? And can we guarantee that not just a single, but all the IoT nodes in the critical infrastructure can get enough energy to operate? In general, when we harvest energy, we need to rely on intermittent operation, meaning that we cannot be active all the time. There are many challenges in the harvesting process, and so what we are proposing here is not just to do the conventional passive way of harvesting energy, but doing active energy networking, so directing the energy to those nodes who might need energy, and this is something that we will be discussing today. Usually, I'm mostly focused on indoor operation, which is quite a representative scenario for critical infrastructure. What are the typical sources, particularly light, but we can use RF, we can use thermal variations and vibrations, and altogether, the amount of energy that we harvest is relatively small, and once again, we need to resort to this intermittent operation. And from all the sources that I mentioned, the light is the most promising for many reasons, for the amount of energy that we can harvest compared to radio frequency vibrations and temperature differences and so on. And also light, as long as there is light, most of the environment have light. It is stable, but still you can see as an example, like the distribution of illumination in a room is not even. And if you imagine there are some plots for a square room where we have 4 luminaries, we can see in this tree graph how the light or the illumination level is distributed at the floor level. The one on the right-hand side, the one in the center is at 1 meter, and the right-hand side is on 2 meters. We can see that if we have a distributed network of IoT devices, some of them could be in a corner or in some positions that they cannot get enough energy. On top of this, there could be blockings by furniture, moving people, and so on. But some of them could be in really good positions and that they could harvest enough energy. And so one of the principles of the energy networking is to treat energy as a resource that we can share and we can network. And those devices who have excess or surplus energy, they could create energy links to the other devices. So we have been doing lots of experiments with this. The opposite is, as I said, what we are doing today, some sort of passive energy networking. Like we passively, depending where we are, we are able to harvest energy, but we cannot guarantee that across the network we will have enough energy to operate. So this passive energy networking is some sort of opportunistic approach. I don't know if you can see in the table there, it is quite small, but you can see a comparison between the amount of power density that you get from light, radio frequency, vibration, and thermal gradients. Particularly comparing light and radio frequency, you can get like 3 orders of magnitude more power density. So this is quite important. And that was the reason that we have mostly used light as a way of networking energy, harvesting and sharing energy. But we have also compared, as you will see soon, other schemes. So who in the system will work as an energy source? Of course, the luminaries, first of all, but then the IoT nodes themselves who have enough energy, and on top of this we can have energy beacons, some particular devices that we add in the environment to provide energy links to those nodes. So they are kind of auxiliary elements of the system. And mostly we have been interested in our research and experimental research as well on the possibility of IoT nodes share the surplus energy with other nodes. And how can we do this? We can do this in different domains. We can do this in the inductive domain, so by inductive coupling or using some induction system, we can transfer like node-to-node energy. We can do it with radio frequency. We can do it optically. Again, we found that the sharing energy from node to node is the most attractive for a number of reasons. And I think I don't have time to go into more details about this, but we can create light beams that could be non-visible if we use infrared, or it can be visible, and they could be narrow beams or wide beams. If we use narrow beam, we concentrate energy. We are very efficient in exchanging or transmitting energy, but we need some special synchronization or alignment. If we have wide beams, the synchronization is not so critical, but we can collect less energy. So the architecture for this energy transfer, we divide it in two ways, like the vertical energy transfer, meaning the energy that we get from the luminaries to the devices. And then those devices, particularly those who have excess energy, they become a donor of energy and then transmit the energy horizontally to nearby devices. Of course, we are assuming that we have a relatively high density of nodes and the mean distance between nodes is relatively small. And this is quite typical in manufacturing in many scenarios related to critical infrastructure. And these are some experimental devices that we have built, like a cube. And on each side of the cube there is a PV cell. And each of the PV cells is harvesting actually light energy. There is also a transmitter. And so these devices are collecting energy, and those ones who are in good position from the point of view of energy harvesting, once they can share energy to other devices, nearby devices. Once again, we can do this in a node-to-node or node-to-multiple nodes, multicast or unicast or so on. And in this case, we have studied the transfers, once again, using light, like node-to-node energy transfer, or using the inductive loops. So what are the benefits for the critical infrastructure? Once again, sustainability, because we come up with a solution not require the use of battery, but still resilient enough to get enough energy to operate. So this has an impact on the cost efficient and the maintenance and so on. And we have identified several suitable scenarios for like logistics, healthcare, aviation, and so on. And so if we see now this idea of using energy in the same way that we are using as communication engineer data, how to network in energy. So we think that this is a quite interesting idea that can be exploited, like considering energy as a schedulable resource. So by doing this, we can also create beforehand energy profiles in the network. If we know that certain, in the future we have to do certain tasks, or it is likely that the certain tasks will be required, we can distribute beforehand energy and create energy profile across the network by using energy networking. And of course, this could be combined, and we also did, as a part of our research, joint data and energy networking. So not only energy, but using the same infrastructure for energy, but also for data, which makes a lot of sense. So the conclusion of this is we can extend the common use of passive energy networking, so passively harvesting energy without doing anything else to support this, with active energy networking, and so this will help making the IoT solution more sustainable. And we have discussed about the advantages from the sustainability point of view and the resilience point of view. I think this is it. If you have any question, I will be more than happy to answer. Yeah.
Yes, thank you. Heidi Himmanen from Traficom. Very interesting. I have problems of understanding maybe the relationship between the zero energy IoT and the critical infrastructure. So maybe you can educate me. To me, IoT is like best effort. And especially if we talk about zero energy IoT, where you need to harvest energy, it sounds like best effort. So as a spectrum manager, that's like the lowest reliability you can have. Yeah. And critical infrastructure is the highest reliability you can have. Yeah. So can you explain this paradigm to me?
Usually sustainability, as this is part of sustainability, is conflicting with resilience, because resilience calls for typically advanced solution, use of diversity or redundancy, which costs a lot in terms of energy and other aspects. And I forgot what I was going to say. And the so what was the question? Sorry, I have. Yes, it is the best. Yeah. Of course, we put all the effort to have a truly resilient system, but it costs a lot. So we want to see if we can still be resilient, but being conscious on the cost and trying to use this energy. So trying to not just to put more infrastructure and complexity, and to be sure we want to investigate if having some complexity, like we have some additional complexity, we could at least be more resilient, but still try to be sustainable just by avoiding use of batteries and the cost involved with that. Yeah. Yep.
Hello. The presentation about the basically routing of energy sounds very interesting. So in your experiment, how long distances can a link be? And what is your loss if you can do over multi-hops? So what is the loss per hop then?
Yeah. In principle, we can do multi-hop, and we have done this it depends. In the laboratory, we have tried like 60 centimeters, and we have tried also even a meter. And of course, if you allow enough time, you can, maybe you could do some of these things at night time. But I think we haven't tried with distances more than 1 meter. But some inductive techniques using the resonator supports even a longer distance, also radio frequency, but with radio frequency, the amount of the efficiency in the transfer is of the amount of the energy that you can transfer is very small. So you will, if you allow enough time, you will be able to transfer enough energy. And of course, there is a duality with data and energy transfer, and we can use protocols, but the main difference is the timeline. That in data we talk about milliseconds or microseconds. Here we talk about minutes to hours. But still, it works. And we did some experiments with multi-hop, and it does work, but it is considerably slow. Yeah.
Right, so we conclude our today's afternoon session, and with that I would like to thank Marcus and also all the other speakers.